In this video, I'll go through some exam questions on the topic magnetism and electromagnetic induction. The first question says, the diagram shows a model used to generate electricity from water waves in a tank. So it's a model. A board floats on the surface of the water in the tank. The coil of the wire is fixed to the floor of the tank. A magnet is suspended from the board inside the coil. So the same information has now been displayed to you in the form of diagram. So if you look at this diagram, you will notice here it is a case of fixed conductor plus oscillating magnet. In this case, if you remember, we said our output will be AC. Alternating current. When a wave is sent along the surface of the water, the ball moves up and down. So this means it is oscillating. The ball moves up and down, and when the ball will move up and down, it will make this magnet oscillate. And when this magnet will oscillate, then the magnetic field lines will get cut by this conductor. As a result of this, AC current will be induced in the coil. This graph basically shows how the alternating current changes as a result of the movement of ball. So we'll have to relate this information with how magnetic field lines are being cut. It says explain how this current is induced in the coil in the model. So we need to talk about how the current is induced. That's number one. And number two, it says you should refer to the model and to the label points on the graph in your answer. So we have to take into consideration label points and to the model. So the label points are these. When we will structure answer to this question, we will have to mainly talk about this, how current is induced. But we have to relate that information to the model and the label points on this graph. Now if you look at this graph, it's a current time graph, and I can see as the time goes by, the current changes. So I can see as the time passes by, the value of the current changes. It starts with 0, goes to a maximum value, then goes to 0 again, goes to a negative maximum value, and then goes to 0 again. Our answer to this question will focus mainly on how current is induced, but our answer has to give reference to the model used, which is over here, and to the label points which have been highlighted. Let's have a look. So I can say, starting with this section, I can say current is induced when magnetic field lines are cut by the conductor. Now we have given some information about this section are being cut by the conductor. So I can say if more lines are being cut, then bigger current. I can say current will be higher if more lines are being cut. I can then say current will be smaller if less lines are being cut. I can also say current will be 0 if no lines are being cut. Then I also have to, because it says you have to mention about the label points as well. So I can say our current is always AC, alternating current. Now I can look at these points and I can say at location O the current is 0, at location Q the current is 0, at location S the current is 0. So I can say here Because the current is 0, no lines are being cut. So the locations are O, Q, and S. This means magnet is not moving. Then I look at the value of the current, and it is maximum at P and it is also maximum at R. So we are saying if more lines are being cut, then the current will be higher. So we can say at P and Q, maximum field lines are being cut. That's one. But if you look at this section here, the current is positive. Here the current is negative. So we can say magnet is moving in opposite directions. We can also say one more thing here. At location Q, the current goes from positive to negative. So we can say at Q, direction of movement is changing. Now I need to add one last bit to it, and that's something very, very important. I've been talking about the field lines, but we are looking at the current being produced, so we have to mention that these field lines are being cut in 1 second. So I said here at P and Q, maximum field lines are being cut. I have to add in 1 second. And this is an example of an answer which will get you full marks on a question like this. So remember, if a question like this appears in your exam, make sure you read the question carefully and then structure it according to the information that has been given to you in the question. Let's move on to the next question. Now the next question talks about plotting compass. Says a student uses a plotting compass to investigate the magnetic field around a wire. So the moment I see this, I'll recall it has to be circular in shape. Number 1. Plus, we will use right hand grip rule to determine its direction. Right hand grip rule. Figure 10 shows the magnet compass needle when there is no current in the wire. No current means the wire is not an electromagnet, but once the current goes through it, it will become an electromagnet. Says which of these shows a possible direction of the compass needle when there is current in the wire going from P to Q. So the current is traveling from P to Q in the upward direction. Imagine this pen is representing the wire. So when I apply my right hand grip rule, I'll have to hold this pen in such a way that the thumb points in the direction of the flow of current. So the current is going from bottom towards the top. I'm going to hold it like this. Now if I hold it like this and if I look at it from the top, I can see from the top the field will be anti-clockwise. The field will be anti-clockwise. So if I was to do that, the field will be circular in nature and it will be anti-clockwise. So these arrows are representing the direction of the needle if you place them at these locations. In this case, our answer will be A. Now, next question says, describe how the student could develop the investigation to find the shape of magnetic field produced by the current. So we've already seen one thing here, that in order to determine this direction of field, what we'll do is we'll make use of right hand grip rule. But this is qualitative analysis. What if we have to prove that this will be valid if you perform an experiment? What kind of experiment are we going to do? I will make use of plotting compass and I will say put mark next to the needle of compass. Then I'll say move compass over the marked point. I'll call it 1, I'll call it 2, and repeat step 1. Then number 3, I can say repeat 1 and 2 until needle is over the previous mark. And then you will connect dots. The same process can be used to determine the field around a bar magnet, but there will be one difference between the two. Because in case of the field around the wire, it is circular. So if you start from one location, if you keep going, you'll come back to the same location. This will not happen in case of bar magnet. So you'll start from one location of the bar magnet and you'll end at the other end of the bar magnet. Once you end, then you join the points together. After that, you'll have to follow the same procedure, but from a different location on a bar magnet. Next question is another 6 marker. The question says, high voltage transmission cables and transformers are used in the national grid. Explain how using high voltage transmission cables and transformers allow the distribution of electrical power around the United Kingdom to be as efficient as possible. So here when I look at this word efficient means they reduce power loss. This is what we have to consider in our answer. While we are looking at this aspect of our answer, we have to give reference to the following equations 1 and 2. So this is my power equation and this is my transformer equation. Before I go ahead, if I quickly draw a small diagram here, this is my powerhouse. Next to the powerhouse, we have step up transformer. Then from step up transformer, we've got cables, which are high voltage transmission cables. Here I have got another transformer, which is my step down transformer, and then it goes to consumers. We now know that these transmission lines are very, very long. This means they will have very high resistance. So if I look at this equation, it tells me when the wire has current in it, there will be some power losses. Now we can't do anything to the resistance of this wire, but current can be changed in this wire with the help of transformer. So I can say in transmission line, power is lost as it has resistance, but I have to say the resistance is high. How do I know this is? So the power loss will be equal to I squared times R. Then I can say to reduce this power loss, we use step up transformer. Next to powerhouse. What does step up transformer do? It increases voltage and it lowers the value of current. How do I know this? This is based on this equation because this is my transformer equation. I can say Vp times Ip will be equal to Vs times Is. Low current means less loss of power in transmission line. How do I know this? Again, P equals I squared times R. Now, so we've gone through this section, we've gone through this section, we've gone through this section as well. We now have to look at the step down transformer, which is before the consumers. So I can then say high voltages are dangerous. Therefore, step down transformer is used before consumers. What does it do? It lowers voltage and it increases current. Then the electricity is supplied to the houses, but you have to remember, compared to these transmission cables, the cables in our houses are very short. They'll have less resistance, and if they have less resistance, then the power losses will be small. You can say cables are short, therefore low R. Hence, power loss is lower. This is the structured answer for this question. Remember, annotation is very important while you're reading the question. Like I did some annotation here, one, and I did this. If you recall this information, it will help you come up with a better answer. This question is again related to the use of plotting compass to determine the field around a bar magnet. So the question that we looked earlier was about the field around a wire which is carrying current. This time it is around a bar magnet. It says a student uses a compass to investigate the magnetic field near a bar magnet. The student places the compass near the bar magnet as shown in figure 6. Mark the north pole of the bar magnet with an N in figure 6. I told you earlier that this plotting compass is just like a north pole. So in this case, it is being repelled by this side of the magnet. And we know like poles repel, unlike poles attract. So if this is being repelled, this will be north and this one will be south. So I'm done with the first part. Next part says state two ways in which the investigation could be developed to show the shape of the magnetic field. To show the shape of the magnetic field around a bar magnet. You may add to figure 6 to help you with your answer. This could also be a 6-marker question in exam, so make sure you are listening and doing what is being told to you in this question. They've already done two things for you. A bar magnet, and they've traced around it. So they've marked the boundary on the paper in case this magnet gets moved, then you can place it back. And they've placed the plotting compass at one end of the magnet. All you have to do is just place a mark next to the needle. So we will follow the same steps that we did on the last question. So we'll say mark point next to the needle. Then you will move compass over needle, move compass over the marked point and mark point next to needle again, and mark point next to the needle again. Say repeat 1 until you reach the magnet, then join dots. then you will say repeat 1 and 2 from another location, and that's it. Next question says figure 17 shows the output from a battery. So if I look at this current, this is DC current because it is always above 0. It's not because it's a straight line, it is because it always has a positive value. It says explain why a transformer will not work with the input current as shown in figure 17. So you need to remember, transformer requires input current which is AC. Why? Because it requires changing magnetic field. Now these both are not possible in this case, so I can say this DC can't produce changing magnetic field. So this point is must. You can say this one is 2 and this is also 2. So you can use either of them. When you both, you can choose one of them and that would be your answer. You can say this and this, or you can say this, or will get you the 2 marks. Next question. A transformer has 30 turns. So this is my number of turns on the primary coil. So this is NP. And 150 turns on the secondary. So secondary means these are my N. A potential difference of 25 volt is applied across the primary. So this is across the primary. So this is my V primary. Calculate the potential difference across the secondary. Across the secondary means I do not know the value of Vs. Use equation selected from the list of equations at the end of this video. The equation, transformer equation, linking the number of turns with the potential difference is Vp over Vs equals Np over Ns. All we have to do is just plug in the values and solve, and you'll end up with the answer. So Vp is 25. V secondary is not known. We'll keep it as V secondary. N primary is known as 30 and N secondary is known as 150. So if you solve, you can say you will cross multiply them and that will give you 25 times 150 equals 30 times Vs. We need to make Vs our subject. I can divide both sides by 30. This is gone and you will end up with the value of Vs from here, and that will be volts. Now remember, this is a step up transformer. How do I know it is a step up transformer? Because I've got more turns on the secondary side. So this value of V will be more than 25. Next question. Figure 11 shows the shape of the magnetic field near a bar magnet. Draw an arrow on the field lines in figure 11 to show the direction of magnetic field. So we said direction means we have to bring a north pole. So if I bring a north pole here, it will be repelled, so it will go away. If I bring a north pole here, it will be attracted towards the south. So I can say in this case, the field lines are like that. In this case, they will be pointing away. It says place a letter X on figure 11 at a place where the magnetic field is strongest. Magnetic field is strongest means if you place a north pole, at which location will it experience the strongest force? So strongest force will be experienced next to the poles. So it could be this location or this. Both are acceptable. Now next part says describe two differences between magnetic field shown in figure 11 and a uniform magnetic field. I'll put a star on this question because it's an important one. So I have to recall what do we mean by uniform magnetic field. So if I recall, I can say this is north, this is south, and the uniform magnetic field will be like this. D, D, and D. If I compare these two, I can say in case of uniform magnetic field, they are always straight lines. So annotation really helps, number one. Number two, I can say in this case, you can see the distance is different between them at every different location. The distance between the field lines is different at different locations, but here the distance is always same. So I can say they are equidistant. I can also think about this, that these field lines are all parallel to each other. So I can say they're all parallel lines. And the most important bit we have to remember about the uniform magnetic field is force experienced by the magnetic material will be independent of its location. I can say, in other words, I can say same strength everywhere. So no matter where you place the magnetic material, it will always experience the same amount of force. This is the most important one that you have to keep in mind. Next question. Figure 13 shows two metal rods carrying a current. So I've got two metal rods and they are both carrying current. A metal roller touches both rods and completes the circuit. Completes the circuit means the current flows through the metal roller. The roller is in the magnetic field produced by the magnet. So what we basically have done is we've got a permanent magnet and we've got an electromagnet. When the current passes through this roller, it will become a magnet. So when you have two magnets, they will interact and they will experience force. Now in this case, this is fixed, but the roller is not fixed. So the roller can move left or right depending on the type of force it will experience. So here it says, describe how Fleming's left-hand rule can be used. And it's a describe question. Can be used to determine the direction of force acting on the roller. You may draw a diagram to help you answer. So we need to remember there are three things that you must remember for this. We've got three fingers. We've got thumb, we've got first finger, and we've got second finger. So the thumb is always in the direction of force. First finger is always in the direction of magnetic field. And second finger is always pointing towards the direction of current. And one more thing that you must remember, they must be at 90 to each other. Very important. If you write this information, you'll get full marks because this is a describe question. Now the next part is about using this. Draw an arrow on figure 13 to show the direction of force acting on the ruler. Now what I recommend is don't use these three fingers together. Only use one finger at a time. So in my case, what I will do in this case is, first of all, I'll determine. So it says current out, current in. So inside the roller, the current is going in that direction. If you apply Fleming's left-hand rule to this diagram now, with using one finger at a time, starting with the first finger, then the second finger, and then the thumb, you will notice that the force experienced by this roller will be to the right. So the roller will move towards this section. The roller will move to the right. Next question is about quantifying the force experienced by a conductor carrying current in a magnetic field. It says a wire is placed at right angles to the Earth's magnetic field. The wire is 0.600 meters long, so this is my length. Now may require unit conversion. Remind yourself, require unit conversion. And the current it carries is 93.1 milliamps. So we can't use this value. It has to be 93.1 divided by 1000. This is coming from key concepts. And the force on the wire is 1.11 times 10 to the power of minus 5 newtons. Calculate the magnetic flux density. This means B is not known. There are 4 variables in this equation. They will give you any 3 and they'll ask you to find the 4th one. So in this case, I can say the value of force is 1.11 times 10 to the power of minus 5. I do not know the value of B. I'll keep it as B. The current is 93.1 over 1000 times by 0.600. If you solve this, you'll end up with a value of B, and that will be in Tesla. You can plug this in your calculator. It'll give you one answer, and you will have then 1.11 times 10 to the power of minus 5 equals B times 0.05586. Divide both sides by this is gone, and it will give you the answer. Next question again is about a transformer. So this is a typical transformer. What is happening is we've been given primary coil, we've been given input voltage, we've been given secondary coil, we have not been given output voltage. But one thing that I can see in this diagram is secondary coil has more turns, therefore it will be step up transformer. Says state the purpose of transformer shown in figure 18. So if it is step up transformer, it will increase voltage and lower current. Next question. There's a changing magnetic field in the core of transformer. So changing magnetic field in the core of a transformer means when you supply alternating current here, then the current is always changing, and if the current is always changing, that means the magnetic field is constantly changing too. So describe the cause of the changing magnetic field in the core of transformer. So the cause of changing magnetic field is AC, alternating current on primary side. So 1 mark will be for saying that it is AC and 1 for identifying that it is on the primary side. Next question. Figure 17 shows a diagram representing a loudspeaker. So in case of loudspeaker, you have to remember our output is force and our input is AC. Explain how sound is produced when an alternating current is supplied to the coil of the speaker. They're saying how sound is produced. This is about sound, producing sound waves. So let's have a look. We'll say when you supply alternating current, what will happen? The coil will become electromagnetic. But in this case, because it is alternating current, the magnetic field will constantly change here. Sometimes positive, sometimes negative. So I can say number 1. AC current produces alternating magnetic field in the coil. And then I can see this coil is in permanent magnet. So I can see coil is in field of permanent magnet. I can then say force is produced causing the coil to vibrate. Why will it cause it to vibrate? Because this force will be alternating. Why? Because the force is constantly changing direction. Now when the coil will vibrate, what will it do? It will cause air particles to vibrate, and this produces sound waves. So one of the important questions in your exam, instead of giving you a loudspeaker, they may give you a microphone. So the only thing that will be different in case of microphone will be your input will be force and your output will be alternating current. Next question. A student has a bar magnet, a piece of iron the same size as the magnet, and some paper clips. Describe how student could use these items to demonstrate temporary induced magnetism. So when they are saying temporary induced magnetism, they're trying to say, show that the iron will become magnet only if it is next to a magnet. Once you remove the magnet, it will not be a magnet anymore. So I can say this will be my magnet. Here I'll have iron, and then I'll pick some paper clips. So I'll say attach iron to the magnet as shown. Then I'll say pick paper clips from iron side. Number 3, I can then say remove bar magnet. The clips will fall. What does that indicate? That indicates that iron is only magnet once it is placed next to a magnet or close to a magnet. If you remove the magnet away from the iron, then iron will not be magnet anymore. Shows induced magnetism. Which one? Temporary. Okay, that was the last question on this worksheet. I hope you will find these questions helpful. I wish you all very good luck with your exam preparation. Thank you and take care.